Well, this is about sequential Monte Carlo. Well, instead of sequential, I have parallel, sorry. And I don't really have any Monte Carlo methods either, but I hope it's fine still. I'm going to start with the background, like the problem that we are solving, in very broad sense. And so these methods for parallelization are based on something called parallel associative scans. So I'm going to take those and then show how to, well, parallelize Bayesian filters by using those kinds of methods, and then also smoothers by using those kinds of methods, and then discuss some implementations in GPUs and then GPUs as well, and then some experimental results. So let's start with the background, and also it's kind of about the notation. I'm going to use very informal notation from applied probability. So I have a state space model, which defines a Markovian model or Markov chain or Markov process by defining a transition density from step k-1 to k. So that's the notation for it. First one, and the second one is the measurement model, which is the conditional density for the measurements. I have everything is Lebesgue density here, but of course you can always say that you can generalize. But anyway, that's the notation. And then the fields, which also define what kind of problems are addressed by these methods. So the typical thing which I have been interested in is target tracking, so that we have something like 6-dimensional state or 10-dimensional state taking values in continuous, well, continuous, let's say 6-dimensional space for the position of velocities. And then we tend to have a very long time series, because you can just turn the sensor on and you sample 100 times a second for a year. So you might have a quite long sequence of placement. And then space applications, they're kind of similar years. In machine learning, you might have like a huge time of states and then long time series or short ones. Speech processing, well, they are audio signals, so like it's like a 44.1K samples. You wait for a year, you get quite long time series. So that an audio signal processing in general. So that, and biomedicine is also about sensor signal processing. But anyway, so the point here is that these time series can be long. So that's what we are addressing here. So there are many efficient algorithms to solve the state estimation problem in these state space models. So in general, Bayesian filters and smoothers are one kind of framework, and then you can interpret Kalman filters and smoothers as a special cases of them for Gaussian models. And then you have various kinds of forward-backward algorithms which come from like a different context, but not the same thing. Or maybe for discrete state systems, but also for like belief propagation. It's also often seen as a backward-forward kind of formulation. So there are multiple versions, and then Viterbi is a classical one which can be used to compute maximum a posteriori estimates in these models. And also it's equivalent to something called max product, sum product algorithms in a certain sense. And then there's sequential Monte Carlo. I think that's the only place why I made a sequential Monte Carlo, but anyway, it's one of the methods that can be used here. But these are not designed for parallelism. So they are methods which kind of start from the time step 1 and go to time step t on the right. And then you need to like take all the steps, so you cannot take shortcuts by default. So they inherently are sequential methods, so they take the OT time to compute, because you need to take OT steps. But that's that is the optimal. Like there cannot be like a lower number of steps in a classical single processor computer, but in parallel computer you can have a better algorithms. So you can have a sublinear methods, in the sense that you kind of process not just start from 1 and go to t, but process multiple things at the same time. so you can actually do better. And here the focus is indeed discussing this type of methods for state-based models or filtering and smoothing in them, and especially methods which are based on something called the prefix sum or prefix sum computations based on the associated scans. And so the context is that nowadays we have like graphics processing units in all the computers basically, and which are huge parallel computers. So it's not really, you cannot really run millions of execution threads this year yet, but you can run like 100,000 or tens of thousands, in a practical, just like every game computer has such a GPU. Hundreds of thousands, maybe it's fine. For millions, well, should have those. So it's quite large number of threads. I recall the time when it was a huge thing to have a 4-core computer. Okay, but anyway, so that it's like a 1 million core computers to me now. A huge thing. So these are very well suited for parallel computing because they have a huge number of computational cores, or computer can run multiple threads. And that's why they are also extensively used in deep learning applications. For example, TensorFlow and those libraries actually support them fully. And but the programming model is different from normal. So they are something called like a single instruction, multiple data, or like roughly that kind of computational model. So that means that actually we need to modify the filtering and smoothing algorithms to be able to use the GPUs in full. And yes, so because of this different computational model or programming model, the GPUs cannot just parallelize any algorithm. So if you run a sequential loop over there, so it will be a sequential loop which will run in one thread. And it's not going to be able to use even 2 threads, but it's just like a sequential as original. So we need to be able to modify the algorithm so that it's decomposes into some kind of sub problems. So that there's like a task 1, task 2, task 3, task 4, which can be done independently, and then maybe we combine the results in the end. And then in the filter, okay, so you really need to do all the steps. So it's not going to be easy, or it's going to be easy, but at least in the classical formulation, it's not taken into account. And what we can use is that surprisingly many sequential algorithms which look sequential at the first sight or glance, so they can actually be parallelized up to logarithmic number of time points by using something called by reducing them to something called all prefix sum computational problem. It's not just all prefix sum, but all prefix operator application. I will actually define the problem later on in the slides. And yes, and the trick also which we are going to use here is that this sum is not the sum operation, but it's an operation that does need to be associative. And the question is that can we do this for state-based? And yes, it will be possible. So there are a couple of steps that we actually need to take first. Is that so we can indeed use parallel associative scan algorithm to get this logarithmic time. So that is one algorithm to compute those all prefix sums fast in logarithmic time. But the downside is that we need to modify the filtering equations and smoothing equations for the Witherby populations. So we need to modify them so that they are associative, because filter is not an associative because you cannot change the operations of the which order you do the time points. So you have certain ordering, and that needs to be changed to make this possible. And but anyway, so once we do this, we get methods which are suitable for GPUs, or then I guess they're like TPUs, NPUs. But anyway, those parallel computers which resemble GPU complex. And for example, TensorFlow, JAX, PyTorch, so they are suitable frameworks for these. Or then, well, we have a Julia CUDA and then C++ CUDA and all those available as well. And so how it will work is that instead of like starting from left and going to right, we actually like do parallel passes on the levels of threes. But we will see that in a moment. So the basis is in parallel associative scans. So let's think about quite simple problem of computing something called all prefix sums for a sequence of numbers. So this all prefix sum just means cumulative sum, just a kind of fancy name for it. So we want to compute these prefix sums or cumulative sums for this vector. And but then the key thing which we can do right away is that actually we can think about prefix sums or cumulative sums of a generic associative operator. So what it means to compute all prefix sums given an associative operator for an array of numbers A1, A2 up to 18 is that we want to compute this kind of vector that contains A1 and then A1 operator A2 and then A1 operator A2 operator A3. So one example is plus, but of course like a matrix multiplication would work. Associative filter will work. So that's the trick which we will have. But anyway, all we need to do is that we need to have an associative operator, so we can change the order of the parentheses like this. It's a convenience if you have a neutral element. So, for example, in plus it's 0, or in multiplication is 1, and matrices identity, or in functions, in some cases delta function and so on. But we don't actually really need to have it. It will appear in the algorithm, but you can do an algorithm trick. You don't actually need to plot it. But so, for example, here we have it. So a simple sequential solution to compute these cumulative sums for an associative operator would be, for example, this one. So we start with the empty prefix sums. It would be a neutral element, and then we loop for k goes from 1 to t, just like compute all the elements in the sum. And this will take OT time, because you take a t steps, and then even with the GPU. So if you just upload the code for it to a GPU, it will run in one thread, and it will take a t number of like a clock. It ticks, how do you say that? It will really take that time, so that the GPU doesn't kind of parallelize anything in here as such. But then someone has noticed that so you can actually parallelize this. So this associative property is actually the key why we can parallelize. So the basic idea is that, okay, so when we do like a compute sums in loop, we actually take like 1 plus 2, 2 plus 3, 3 plus 4. But we don't need to do that. We can also do like a 1 plus 2 first, and then 3 plus 4 at the same time, and then combine them. And you can think about getting a tree of combinations, and you can actually parallelize that. And this will not only for summation it works, but it works for any associated operator, because we use that one. And so we can think of using this recursively to get like a logarithmic height 3. And then we can imagine that maybe there's another, we just get a single sum easily. But then we see that when we compute this, we actually get the intermediate result somewhere in the tree. And then we can think about reordering them back to like getting the actual prefix sums. And still it will take just like a height of the tree number of steps. So that's another pass. And someone has figured this out for us already. And this can indeed be formulated as like a up and down troubles or sweeps in a tree. So consider, for example, computing this prefix sum or cumulative sum of like a number from 1 to 8. And so what a generic algorithm to do this also in practice does is that we can first form a binary tree of these like this. So we have original ones, then we have the pair sums here, and then the sum sums of the pairs, and then so on up to 36. Because well, all these levels can be done in parallel. We can see that so with t numbers, this will have a log t of levels, so we can do this in log t time. It's called span time, which means that how many like a real clock ticks it takes to run it. And so of course, like the real number of operations, so that is linear. So if you think about it, so the GPU will heat up. So it will heat up as much as the GPU would in the sequential computation, because it takes a linear number of actual operations. But anyway, the clock time will be more. Yes.
The tree doesn't contain some of the sums.
Some of the sums.
6.
No, it doesn't. No.
So you need another tree for the other sums.
Yes, it's in the next slide. Yes. And so this also works for like a more general associative operators, but yes, as pointed out, that we need to do another operation, so that we still need to do a down pass. So it's slightly more complicated, but it's just a formal way to like collect the sub operator or sub what is results from here, and then make the other parts of the sums appear. So that this is really the outcome. So we think about adding an L, like a left value over here. So L is 0, L is 0, L is 0, L is 3. This is the kind of thing which you might see in a computer algorithms course descriptions in slides, but this is fun. So that so there's a root has L is 0, and then every left child inherits representative value of L. So here we just inherit a 0, and then every left child. Okay, so every right child gets the left side sum plus current error. Right child gets 3 plus 0, and then here we should have the same rule. So this can be formed by starting from top and then going down level by level, and this can be done in parallel. And the trick is that we will get the actual prefix sum or prefix sums at the bottom here. And so the previous slides we could do in the log t steps in parallel computer, and this way we can do it in log t steps in parallel computer. We can actually compute all these elements, these t elements in log t time. And well, so we don't actually need to form this tree. But there is already like a developed. This is like by Blalock somewhere in 1980, roughly. So that this is like an in-place algorithm. So there's an up sweep, which is just a parallel loop, and down sweep, which is parallel loop, which does this tree traversal already. So, but these are generic. You just give it elements and operator, and run this, compile this into GPU array. Okay, so now we know how to compute prefix sums. So how can we then do Bayesian filter trees? So what we need to see is that we have this classical, how classical, but anyway, a Bayesian filter formulation that we have here. So we start from P or prior distribution somehow, and then we have the prediction step and the update step. This is anyway one way to formulate. But now we can see that this is actually a sequential algorithm of this kind. So that we start with S0, S being the prior, S0 being the prior distribution, and then we compute the prefix sums, and the prefix sum values are actually maybe the filtering distributions, or they could be the predictive distributions. And the question is that can we find an associative operator which will then corresponds to computing prefix sums for this one? Yeah, and yes, it turns out to be the case, and that's the trick. And so without going, so let's review the answer first and see what was the intuition. So what it will look like. is that instead of having numbers, we have these elements actually consist of a conditional distribution of xk, current measurement, like a current state, current measurement, given the previous measurement. So these are the first part of the elements, they're like tuples. And then the other part of the element will be like a measurement given the previous state. If you have been working on Q-filter smooters, you might recognize some of the terms here. But anyway, so we saw these two densities in the element, and then we can define the associative operator like this. So it's not simple summation, it's not simple matrix multiplication, but it's two integral expressions and normalization. So this combines so Fi, Gi, and then Fj, Tj. So the right-hand side, yes, so we compute the new elements Fij and Gij. So the first one is given by, we take the G element, which would be it's function of x, well, function of y actually here, and then we'll multiply this together and integrate over, and then we normalize it. I have a slight intuition for it in the next slides, because it's a bit hard to see, like you see the answer, but okay, so but the process of getting into that is more. And then the G will look like this, and you can show that this operation is associated. And what actually happens here is that, okay, well, let's not skip into actually happening there. But what happens here is that if we apply this operator, so we have a A1 operation, A2, and then up to AK, we get a pair which contains the filtering distribution, well, which is the filter, and then normalization constant. Well, to be very precise, if we just look at the equations, okay, if I look at the equations, I know that we actually get like xk given y from 1 to k given x0. So we need to do a bit of trick and define one of the elements to be already marginalized over x0. I just want to be precise. It might not be make any sense to you, but if you actually check the equations, you will need to define the element A1, then everything matches. But then what actually happens is that we are really just doing like a skip connections between time steps. Is that so assume that we have this kind of condition distribution, so that this one is okay. So the lower one is like xj given xi, and then given all the measurements between. And because this is Markovian, kind of this previous history of measurements doesn't matter, so it's kind of conditioned on all the measurements up to j now. But Markovian property does that makes them disappear. And then we have the measurements on the whole range given the starting point. And then we have another one for the second part. So the end point given the middle point and the measurements there, and then the measurements given the starting point. It turns out that we can, it's like a jump from here to here, here to here. And these associative operators actually they compute a skip connection. So they just compute these corresponding ones for this longer. And it turns out that that operation is given by these. So if you plug in the distribution, so even in my notation, it becomes a mess, but anyway, so that's what they do. So it's skips, and then because these distributions are exactly enough to compute this new distribution. More explicitly, so the relations are just quite simple integral. So you can derive this by using the Markovian properties. So this is more like the associative operator when I plug in the distributions there. So in practice, how we can use this is that so we first compute the initial elements, which were like a very local conditional distribution of like xk given the current measurement and the previous state. So that those can be done in parallel for each local place. And then we have the corresponding measurement given almost the same state. So this can be computed in parallel also. Like sort of we don't need to like look into other time points. So it is constant operation in the sense of span complexity in parallel computer, because regardless of the length of the time series, we can do everything in parallel. Of course, the catch is that we might run out of core, but okay, let's not think about that. In principle, it's O1. And then we run our parallel associated with scan algorithm to compute all the prefix sums, and all the prefix sums will be the filtering result and the normalization constants. And well, the challenge is that we need some way to present this F and G, which is always in Bayesian computations. And it turns out for linear Gaussian and finite state cases, we get explicit representations, but otherwise we need to approximate. It's hard to approximate sometimes. So for Kalman filter, we will get something like this. So that this is the model dynamics in my notation is that so it was a linear function of x and then fixed covariances, and then a function of x in the measurement model and fixed covariances. So the representation can be like this, so that we need to parameterize this distribution, and how we can do is that we actually parameterize this multiplier matrix here. So this A matrix and then the bias and the covariance. So this A, B, and C will be our parameters for this FR. And then this one, well, if you look at the equation for Y, you notice that it's not going to be normalizable Gaussian distribution. So you need to, or at least one way to parameterize is to use the information form of Gaussian, but anyway, it's a Gaussian. So you can parameterize by like the information vector. It's mean of the information Gaussian, but anyway, that and then the corresponding inverse covariance. So you can parameterize our element A with A, B, C, eta, J. And then the initial elements, so they will be like they can be implemented independently computed, and they are look a bit like a Kalman filter predictions that updates locally. So I don't want to copy the equations here. And the associative operator takes this kind of form. So it's actually quite interesting. You can see, if you're happy working on Kalman filters along, you will see some resemblance of the two filters smoother there. And actually there is also there's a Kalman filter here, two filters smoother here, but you end up like doing both in both directions. And then, okay, so looks like there are two inversions, but actually this one is transposed. But anyway, so these are, like if you have the solutions for jumping from I to J and J to K, then these give the jumping from I to K. So this is the skip connection for that. And yes, so this Kalman filter is already interesting, but you can also do the finite state HMMs, and then this F becomes a matrix and J becomes a vector. Well, that's finite dimensional quantities. And in that context, there's interesting connection to Mealy propagation kind of methods, because you can also see that so we can also format the whole thing in terms of something called the potentials. Well, if you define a potential like this, then this whole thing is just start integrating from the middle instead of the end. So afterwards, everything is trivial, but you can see that as well. And from that context, we can also borrow those max sum methods and max product methods, also the maximizations, and they are related to the Viterbi methods. Yes. But then you can also do smoothers. So the same idea works. So this is so-called, I would call it Ralston-Streibel type of smoother, where you choose the filter and then you do the smoother. But anyway, that one, not the two-filter one. And so we can select elements to be like this. So this is X, K, even the next one, and then all the measurements up to the current time point. And then you can define the operator to be just multiply and then integrate over. And what happens is that in this case, these backward prefix sums. So if you start from K and go to T, then these are the smoothing or marginal smoothing distributions. And well, but algorithmic sense, we can actually define or construct backward prefix sums algorithm in the same way. And what happens here is that, yes, so we have this kind of conditional distribution, which is actually conditioning backwards. We are completing skip connections by using these kinds of distributions. So we have xi given xj, so it's going backwards, and then xk given xj, just a moment, other way around. Yes, so from k to j and then j to I. And then that skip connection is given by this single integral. So that's why the combination rule looked like that. And Gaussian case is again interesting to see. So we can parameterize these by using a matrix, which is the multiplier here, and then biases, and then another matrix, and then the operator becomes like this. So this gives the skip connections from two combination of two skip connections. And yes, so the non-linear extension, it's a bit on the way, but linearization at least works. So that you can do that. So that if you have this kind of non-linear, non-Gaussian models, so first of all, well, HMM could be done, but then another way to go if you have continuous valued states. So one way is to linearize, and then the linearization methods quite often are based on somehow implicitly approximating the transition density as Gaussian. So we compute this F and U and Q using, for example, Taylor expansions over a nominal trajectory, or then those statistical linearizations, which lead to unscented kind of methods. And indeed, in iterative methods, there is a useful way that will be actually like a start from a nominal trajectory, like iterative smoothing methods. So we start from a nominal trajectory, then we linearize, and then we solve the linear problem, and then we linearize again, and then solve the linear problem and linearize again. And these type of methods are very, very compatible with these formulations, because what we can do is that we can, well, linearize, and it turns out that we can actually do that completely in parallel, and then we just apply our linear or affine solution to the problem. So what we can do is that, well, we linearize each of the dynamic and measurements models by using the extended Kalman filter smoother style, and then this sigma point unscented style, or then other ones. And then that can typically be done locally in parallel. And then we can run the parallel Kalman filter smoother to get a logarithmic time complexity. And then we can use the results as the new nominal trajectory. So that's, for example, how the extended Kalman smoother works. And we get anyway algorithm which has a span complexity of number of iterations times log t. So if t is well, one year of audio signal, then this is already much better than just using the linear complexity. So if t is couple billion. But then there's a bit of challenges that this initial trajectory, which is independent of these methods, but this initial trajectory is hard to actually choose in these methods. Yes, so maybe you could use SMC for this as well. So we have some joint work with others here about like a divide and conquer approach. But I think that we never managed to actually use SMC properly here. There are some fundamental challenges. But then implementations, well, in short, you can use CUDA, which is fun to program, but it's a bit tedious to program as well. Because, for example, like you would need to do like associated scans within GPU, and the problem is that, for example, this Numba doesn't support matrix computations at all. Well, C++ would be an option, but it's a bit hard to maintain. Julia has it doesn't support matrix operations within kernels either, because it uses like a Q plus, and that it's so that this is sometimes a bit tedious to program. But then another option is that in TensorFlow has this associated scans already, so that we actually have been using this. So we just define a function which implements those matrix operations, and then you call this. And then Sachs has it as well. And then we also get automatic depreciation support as a plus here. And then someone has been debugging this TensorFlow capability with our method, it seems. It's there actually. Yes, so this is exactly the Kalman filter variant. We also have some codes available. It's well, Aspen has good way in this first example when we other ones. And then the Viterbi codes are here if you're interested. And then what we typically get is that yes, so that when we run this in a CPU, this is in I don't recall how many cores. I guess they might have 10 nowadays. So what happens is that you get a bit of improvement. So because what happens is that well, for example, if you think that you have like a O1 complexity for some operation in a time series of length t, if you only have 10 processors, so you can only do t to 10. So you run out of processors quite soon. So I think that this has like 10, so that we get some improvement in some of the parallelization parts, but then we run out of the cores, and then it doesn't help anymore. But in a GPU, we get much. I think this has more than 10,000 cores. So we can get up to 10,000 with like a logarithmic complexity, but then it will start to grow. I was running this in the call up me. And then results for nonlinear systems. So similar effects. So these are for GPU only. So we get the linear growth and then logarithmic growth up to certain points. This will start to grow once out of the course. But then, like the better the GPUs become, the further we can get in it. And then HMMs, well, they look similar. And these HMM results also, there are always catches, right? So the catch here is, for example, the dimensionality scaling in the number of discrete states if you run this for HMMs. Because instead of just having vectors, you need to kind of combine matrices. So there's a squaring of something. And then also in Kalman filter, we need to have more parameters, and then something scales more badly in the other direction. So we never get something for free. But as a conclusion, so we started with all perfect sums computations for summation operations, so they can be computed in parallel in a GPU using associated scans. But then it turns out that this sum can be any associative operation. And then what I will discuss then is that the inference in probabilistic state space models or like filter smoothers can be reformulated as a sequence of associative operations. And then this leads us to parallel Kalman or Bayesian or Viterbi kind of methods. And then they can be implemented in CUDA on CPU or TensorFlow, and then especially TensorFlow and JAX have already implemented associative scan functions in them. Yes, and here are some references. So most of these are actually prefix sums, but maybe this third last is not actually based on prefix sums because we couldn't solve the SMC case, so that's still. Okay, but thank you.
So